Okay, hello again. Good morning, everyone. So today we're going to finish modeling transformations, and I'm going to start talking about viewing transformations, starting with the camera transformations. So we actually talked about the most difficult modeling transformation, which is rotation around an arbitrary axis on Tuesday, and we are going to go over the alternative method, which we actually covered in 2D. Do you have trouble connecting? Does anybody else have trouble connecting? So Mujella sent me a message. It only came to me. And now it's to everyone. If you have any problem in connecting, we may also try. Maybe we can start. Yeah, let's try Zoom for next week. I'm going to send the Zoom link on Oticlass and also on Cow, and maybe Zoom will have less problems. It may be better maintained than WebEx. Yeah, yeah. Okay, so but yeah, let's try. I mean, for today, let's continue with WebEx because it will take some time to switch to that. But yeah, for Tuesday's lectures next week, I'm going to try out Zoom, and let's see how it's going to work out. And I'm going to send an announcement about this on Oticlass and in Cow. Okay. So this was the rotation around arbitrary axis. The recording is on. Okay, so and let me also get my whiteboard up here. GIMP. All right, new one. Let me resize this. All right, so in order to rotate, basically what we want to do is we want to align our rotation axis to one of the major axes. And the way to do that is we first translate, so the rotation axis is given to you with 2 points, P1 and P2. You either move P1 or P2 to origin so that your rotation axis passes through origin. And actually, for example, in OpenGL, for example, there's a GL rotate function which allows you to specify a vector that passes through origin. So it doesn't, the rotation axis in OpenGL is not specified by giving 2 points. If you look at, for example, the OpenGL manual, OpenGL rotate, if you look at the manual page for that, you're going to see that. So GL rotate F. So this one, oh, this is like a Stack Overflow. This is the manual page. So there are 2 functions related to GL rotate. One of them gets double arguments, the other gets float arguments. But as you can see, it only gets an angle given in degrees. For example, I want to rotate 45 degrees, and it just gets 3 values. So with just 3 values like this, x, y, z, you cannot actually specify an arbitrary axis. So the axis is defined in such a way that it passes through origin. So only the point P2 is given. P1 is always taken as 0, 0, 0. So this is the basic rotation OpenGL provides you. But the good thing is that we can actually combine it with 2 translate Fs, GL translate. We can, if we're, for example, if you want to rotate our object around a really arbitrary axis, which is given by P1 and P2, we can first write the translate function, GL translate F. So the transformation that I'm going to be writing is going to be like this: GL translate F, translate F minus P1 X minus P1Y minus P1Z. So if we just first move your P1 to origin and then you do the rotation, GL rotate F, what is that vector you're going to, for example, 45 degrees, imagine that that's your angle. Your vector is going to be just P2X minus P1X, okay, and P2Y minus P1Y. So this will be your vector that you want to. This is the direction, right? Given P1 and P2, so this is the direction of this vector that I'm writing here. P2z minus P1z is the direction of the rotation axis. If it was like this, if this is P1 and this is P2, as you can see, P2 minus P1 gives me this vector. So I want to rotate around this vector, but only OpenGL can only does that when it is passing through origin. So what I do is I move all of my objects first. So I move P1 to origin so that this vector is passing through origin, and whatever this value is, this direction is, I rotate around this vector, which now passes through origin, and I need to translate everything back. So you need to write GL translate F plus P1x this time, P1x, P1y, P1z. Okay, one question you might have is, actually, there are a couple of things you might have noticed. I wrote my C code. This is C code, okay? But as I said, you first do this, I wrote it backwards, right? So here, this is where my draw command, for example, I have a function which draws a triangle. I can write it here, I can call it here. Draw triangle, just specify the triangle vertices in their original coordinates. So there is nothing object-oriented. It's not like we define the triangle first and we say move triangle, do this to triangle. It's not, as I said, it's not object-oriented in the sense that we don't have objects and we don't move them. We don't provide actions on them. We just give the graphics card draw commands, draw these triangles. And when the drawing occurs, the OpenGL just looks at some global settings at that point. Okay, I'm going to draw these triangles, but what is the current modeling transformation matrix? What is the current projection matrix? It looks at these global variables, applies that on the draw command, and then draws it on the screen. So your draw triangle command will just be, is going to draw a triangle object in its original coordinates, not for example, it may be centered around origin or not. It's the original coordinates that you read from the file. You don't need to modify this triangle, draw triangles command in that regard. It's just the original coordinates. But when it's giving these vertices to OpenGL, as I said, OpenGL looks at the current global variables, global settings. What is the current transformation matrix? And then before it draws these vertices, it applies these matrices on those vertices automatically. So therefore, if you want to move some object, you need to first modify your modeling transformation matrix with these commands. And the way they are applied is, so it's like each of these function calls are multiplying a current global modeling matrix on the right. For example, if I have some global modeling matrix, this GL translate function, it does nothing but creates a transformation matrix with these parameters, which is just this 1, 0, 0 minus P1x, 0, 1, 0 minus P1y, 0, 0, 1 minus P1z, and 0, 0, 0, 1. So it forms this 4x4 matrix and multiplies the current modeling matrix on the right with this matrix, and it updates. So it does basically this. The new global modeling matrix is this, okay? So this is what this function does. So instead of calling this function, you could have done it yourself, for example. There are functions that allows you to call get the current global, get the current modeling matrix, and you can store it as some 4x4 matrix. They're stored as one-dimensional arrays, and they are stored in column major order, so you have to be careful if you're dealing with these matrix values yourself, but this is exactly what it does. So since these functions are doing that, your other rotate function and the other translate function, they actually, when I was giving this example, P1, Px, it's plus. So the function call that refers to this first one, as you can see, the parameters are positive. It creates this transformation matrix in which the parameters are positive like this. But as you can see, it multiplies the matrix on the right, which means that when you have this draw triangle call, which have your vertex information in the triangle, as you can see, the transformations that are applied to this vertex first are the function calls that are closest to your draw triangle command. So the order of modification of the modeling matrix is this way. This gives the order of multiplications, but the order of application of those transformation is this. So actually, with these 3 lines of code, you can have your OpenGL program to rotate around any arbitrary axis. This basic GL rotate function only allows you to rotate around an axis, specify the XYZ coordinates of a vector respectively. So this vector actually passes through the origin. Another thing you may ask here is that maybe, so we already moved P1, Py, Pz. So why don't we have here, since it's already moved to 0, why don't we just say just P2 here, it's going to be moved anyway. So it's not, I mean, these transformations, they're not your vertices. You have to specify your vectors correctly. Although this translation of moving P1 to origin is changing the modeling matrix, your axis of direction, your axis of rotation, the direction of the axis of rotation is given by this vector, which if you just write it as this is P1, if when P1x becomes 0, actually this means that your P2x becomes P2x minus Px, so you have to do it manually like this. It doesn't, those parameters that you have are not vertices. So as a programmer, you're responsible on how to specify those parameters correctly. In other words, these modeling matrices, they're not applied on the parameters automatically. You have to set your parameters correctly. So this was the direction vector for axis of rotation axis, therefore we specify it as a vector like this. Okay. When we come to OpenGL, we're going to talk more about these things, but I just wanted to show you that this general 5-step thing, actually, this first step, OpenGL already provides the second step automatically. It doesn't need to be one of the major axes. Although, as you can see in our major rotation matrices are these 3 things: rotation around X, rotation around Y, rotation around Z. These are our basic rotation matrices that we use in the book and in the slides here. If you're going to program rotation using OpenGL, your basic rotation is not one of these. Actually, your basic rotation is rotation around any arbitrary XYZ vector. But if this was your basic rotation matrix, then you have to have this step 2, which after you move your point 1 to so that it passes through origin, we don't know how to rotate around this arbitrary vector. We know how to rotate around X, around Z, or around Y. These are our matrices that we have defined on the slides. So what we have to do is we have to make the necessary rotations so that this P1 prime, P2 prime becomes aligned with one of the axes. This is what we did last time on Tuesday. So I'm going to skip those parts, but if you have any questions about this part, if you studied these parts, and if you have any questions about the rotations we do, why we are performing 2 rotations, if it's not clear, again, let me try to demonstrate after your object passes through origin. So there are 2 angles basically. One of them is to get it down, and the other is to align. It's not. So right here. Let me use this side again. So there are 2 angles. For example, this angle, as you can see, is a small angle. It may be inclined like this, a small, like a maybe 25-degree angle like this, but it may be a large angle to put it down. So you may want to rotate around the x-axis like 85 degrees to put it down, and then maybe 20 degrees or so to align around the y-axis. Now it becomes aligned with the z-axis. So there are these 2 angles, alpha and beta, that was on the slides. Now the alternative method, on the other hand, is actually much easier than the other one. It doesn't deal with angles. We don't need to, I mean, in this one also we don't deal with actual angles. So this alpha and beta, we form these rotation matrices ourselves actually. We don't, if you look at this, we are not using any arc sine, arc cosine, or arc tangent. This rotation around x alpha degrees, we just make use of the definition of alpha as, for example, the side that is closest to the angle, one side divided by the hypotenuse. So that's we use the definition of sine and cosine, and we just use the lengths of these vectors to find the sine and cosine. So cosine beta is just given as the length of this projection on the yz plane divided by the length of the entire vector, which is 1. So this is what we do to write those matrices. So it's again not angles, but it may be a more difficult method. The alternative method, on the other hand, is this orthonormal basis method. This is the general method is like this, and we are going to be using it for camera transformation as well. So if your goal is to make a rotation such that, for example, if this is your world coordinate, x, y, z, okay, this is z, so let me use the general convention that we're used to. I mean, this could be x and z, and I mean, x and y. In that case, yeah, this could also be possible. If this is x, for example, and this is y, I think z would be the other way. So I should have drawn, for example, if I draw something like this, this is x and this is y, where would positive z be pointing at? Just imagine this, you're looking from, for example, top right. So this is what positive z would be, right? If it was, this is x and this is y. Anyway, so let's use the regular convention that we are just looking at our image plane is parallel to the xy plane. In that case, positive z is pointing towards us. So imagine we have another orthonormal basis vectors which are orthogonal to each other, and they are in any orientation. For example, this may be our x prime, y prime, and z prime vectors. And this x prime, y prime, z prime will be defined as vectors, as unit vectors in this world coordinate system. In the world coordinate system, for example, this x direction is this vector, 1, 0, 0, this y direction, which we call, sometimes this is u, v, w, these unit vectors. 0, 1, 0 specifies the direction like this, and 0, 0, 1 specifies the direction in the positive z-axis. So if our goal is to align, for example, to perform a rotation in this new coordinate system, let's call this a new coordinate system, NCS, okay? We are going to name them as camera coordinate system, like CCS, or viewing coordinate system, VCS. You may see this in the camera transformation case. But imagine we have a different coordinate system, which is given something like this. For example, Z prime, maybe, let's see what Z prime could be. It could be, for example, let me give something easy. It could be like 0.6, 0, and 0.8. Could be Z prime. And Y prime could be still 0, 0, 0, 1, 0. And X prime, sorry, so this is I wrote this one as Z prime, this is Y prime, and X prime will be 0.8, 0, and minus 0.6. Look at this. So there, as you can see, I have defined a new orthonormal basis vectors in such a way that they're all orthogonal to each other. I know that these two vectors are orthogonal to each other. The dot product of any pair of these two gives you 0. So they're all 90 degrees to each other. So this is x, so it's still to the right, but a little bit behind in z direction. So it has negative z component, positive x component, and here's z prime. As you can see, it has some x component. This vector is not directly pointing towards us, a little bit towards right. So it's like the entire coordinate system is rotated. But the thing is, the coordinate system, we may also have specified an origin for this. So these vectors themselves, they cannot define the position of the coordinate system. So for example, this position here, which may be 9, 3, maybe -2. If this point 9, 3, -2 is my new origin, I need to also specify this in addition to these vectors. The vectors themselves, they just give like vectors which you can place anywhere. In other words, like here, this may be something like this. So z prime is something like this, x prime is something like this, and y prime is the same as y. So it's like the whole entire world coordinate system is tilted a little bit towards right. Okay, so these vectors, as you can see, they just give directions. Now, here's the thing. If you want to align, if z prime, x prime, and y prime with x, y, z here, the rotation vector that aligns this one on world coordinate system is given by writing these in the first, second, and third row. Okay, and the last row is again 0, 0, 1. So this is 0, 1, 0, and z prime is here 0.6, 0, 0.8. So this rotation matrix rotates whatever object you have here. For example, it performs the rotation such that this is aligned with the world coordinate axis. Okay, it performs this rotation. So what we need to do is, if we form these vectors in such a way that one of them is our axis of rotation. For example, if this is P2 and this is P1, if we can form this P1, P2 such that it's going to be z prime, and if we can form these two additional vectors such that they are both orthogonal to this vector from P1 to P2, then we can form the single rotation matrix to align our axis of rotation with world z. So this is exactly what we do, and there are multiple ways to do that. You can define, because here, as you can see, just as a single vector does not specify a unique coordinate system. Just given P1, P2, you can have infinitely many coordinate systems that are, for example, you have this x prime and y prime, they can rotate freely around P1, P2 vector, right? They will still be, it will still be orthogonal to to each other, and also to P1, P2. So a single vector like this P1, P2 does not uniquely define an orthonormal basis, okay, from P1 to P2. So there are many heuristics you could use. So how do you define this x prime? But after you define one of those, after you define an x prime, if x prime and z prime is defined, y prime is uniquely defined as the cross product of x to z, for example. Okay, so therefore the first thing is, if you look at the first step, just say it's a heuristic saying that to find v, set the smallest component of u in an absolute sense. Whatever the smallest component means that in terms of you look at the absolute values of these ABCs, whichever is the smallest, you set it to 0, so that you have your vector in such a way that it's when it's multiplied with this, because switching these two and multiplying cross-producting with this is always going to give you a vector which is orthogonal to this, and it's setting the smallest one to 0 is you're just making the one that is most closer to one of the major x's 0. Okay, so if you have some ABC and assume that C, without loss of generality, C has the smallest absolute value among these, you have your V vector as minus B A 0. So you just set your V vector with an heuristic, setting one of those three values to 0 and swapping the two and negating one of the others. And it could be, for example, you could have make this B minus A0. That will also be okay. Okay, this, for example, V could be B minus A0. That's also that will also work. It doesn't matter. At the end of the day, we are going to have our ABC. U here is our ABC, which is the direction of the rotation axis. And these are, so in other words, A is P2 minus P1x, B is P2y minus P1y, and C is P2z minus P1z. So this vector we obtain. This is the direction of rotation. And at the end, we are going to rotate around U, around X at the end, because this is our rotation axis. Then this V and W will not matter. Okay, you can set them any way you want. This corresponding, so but they have to be orthogonal to U. So this is one way to make it orthogonal. After you have the V vector, the cross product of U and V gives you W. You normalize these values V and W, and yeah, this slide also said, note that we're just finding one of the infinitely many solutions. So there are infinitely many solutions in which U is one of the basis vectors of an orthonormal basis set of triplets of vectors. After we have that, we rotate, when we use this matrix, our rotation aligns everything such that U is aligned with the x-axis. Now, then we perform a rotation around x, because our rotation axis is now the x-axis. We can rotate around x alpha degree, theta degrees if theta was our input, and then we need to undo this initial rotation, which will be the inverse of this matrix. And finding the inverse is really easy for orthonormal basis function. It's just a transpose. So the inverse is equal to the transpose of this matrix. And that's the alternative method, basically. Okay. Any questions about the alternative method? So the final rotation matrix, it will be like this. These two steps are simplified as a single step. We still need to do the translations. Okay, so we need to do the, yeah, here it is. We first translate P1 or P2 to origin, then perform the rotation to align the axes in one step. So it becomes the same 5-step method that was shown on the first slide. And we perform the rotation around the x-axis, theta degrees. Now you may ask, why do we do around the x-axis? Could we could actually set up these orthonormal basis functions so that our direction of rotation is aligned with the y-axis or the z-axis. Okay, so depending on how you form your rotation matrix, if your u values appear in the first row, second row, or third row, you can rotate either around x, y, or z. Doesn't again, it's one of the many alternative possible solutions. Yeah, that's the most difficult three-dimensional modeling transformation. Then in terms of scaling, it's a simple extension of 2D. We just have a third parameter sz, which allows us to scale in the z along the z-axis. To scale with respect to a fixed point, we first move that fixed point to origin, then do the scaling and translate back, the same thing as in 2D. So I'm just skipping these quickly because it's the exact same thing we have seen in two-dimensional rotation. Reflection also very similar. Reflection around, this is if you want to take the mirror image of a vase around the YZ plane with respect to the YZ plane. If the your mirror is in this direction, you just invert the x coordinates, or you invert the z coordinates in this case, or the y coordinates if you invert it like this. So how about reflection over an arbitrary plane? Again, we need to first do the transformation, the translation, which may include translation and rotation, so that our arbitrary plane is aligned with one of the major planes. If you were given an arbitrary plane, just move the mirror so that it is exactly aligned with one of the major planes, then perform the reflection, then move your plane back. So this is how we would do a compositely reflection around an arbitrary plane. Okay, the final thing in modeling transformations here is how do we transform normals? There is both in OpenGL and when we are going to do GPU programming, there is a matrix that we will be using. In addition to this modeling, viewing, and projection matrix, there's a matrix called GL normal matrix. And there's I'm going to share with you a link with that, the normal matrix. So this Lighthouse 3D is a very nice tutorial for OpenGL and this forward rendering pipeline. It has really nice tutorials, and one of them is inside this GLSL 1.2 tutorial. GLSL is the language we will be using to program graphics programming on the GPU. But so this normal matrix is a different matrix that is used just to transform normal vectors of triangles or surfaces. Okay, so why is it not a 4x4 matrix? It's actually a 3x3 matrix. So this tutorial, I'm going to share this link with you, but it's a really good description on how when we transform the normals. So there's the problem. We have a triangle with a tangent vector here and the normal vector here. When the model view matrix contains a non-uniform scale, which means that x at some point, if you scale your model with different sx, sy, and sd parameters, it will transform the normal in such a way that it will deform it, which will not correctly show the normal of the triangle's surfaces or edges correctly anymore. Okay, if the scale is uniform, if you don't have any non-uniform scale in our code, you don't need to worry about it. You can just transform your normal vectors with the same modeling transformation matrix. But non-scale, non-uniform scales perform this problem. So what is represented here, we are going to see on the slides too, is how we can actually form this correctly by finding the correct transformation matrix. So there's this article I'm going to share with you if you want to read it later, but this one also shows a similar example where if we scale by in the x-coordinate 3 times and y and z 1, this scale, as you can see, does not, when this line segment becomes 1, 0, 1 here, and 3, 0 in this one. And as you can see, if you apply the same scale to your normal vector, it is not uniform. Oh yeah, exactly. That's also a good point. If it's a uniform scale, even if it's uniform, if you scale your matrix, for example, its length will be non-normal anymore. So you still need to do normalization, which will actually take you back its original values. So scale will not be. If when you're using your normal vectors, they should always have unit length, and therefore they should always be, they shouldn't be scaled at all. They should be rescaled back to 1, 1. This actually is important when you're performing rotations to your triangle edges. That's when this becomes important. In that case, rotation doesn't change the length of your normal vectors. But if you have performed a composite transformation matrix which contained not only scale but some rotation and translation, and if the scale that it contained was non-uniform, then this may cause a problem. Yeah, so in any case, we have to normalize our vectors so that they're always their length is always 1. Yeah, that's a good point. So here the transformation is no longer perpendicular in this case, as we have seen. So when we are transforming the normals, we have to solve an equation to find how they should correctly be transformed. So let's just discuss this general case. So if we have 2 points on our surface, A and B, the normal vector, by definition, its dot product with this vector on the surface should always be 0. It should be preserved. And after we transform A and B, even if we scale, A and B may be scaled, this rectangle here may be deformed. It may even be, we may even do shear transform. There may be deformations to this. Even in that case, when this vector is deformed, this normal still should be orthogonal to vector V. So what we are going to do is, if we apply a transformation to these 2 points A and B on the object, the new normal should be found out by, again, it should satisfy this equation that the dot product with this transform one should be 0. So since we know that V prime is going to be given, this vector or this vertex is given by applying the modeling transformation matrix here. This is given. Okay, we are going to modify our vertices by applying the modeling transformations on them. And it should be the case that we need to figure out what this matrix should be. What should Z be, which will be applied on the normal vector N, the original normal vector, and M prime will be found correctly. So Z is the matrix we are looking for. How can we compute Z is what is written in the next slide. So here we can also, this dot product could also be written, so N dot product V, we want it to be 0 in the original case. This is our definition of the normal vector. The dot product can be written as a matrix multiplication in which we transform one of the, if these were both column vectors, you change it, when you transpose it, you make it a row vector, so you multiply this row vector with a column vector, the result is a scalar. Okay, so you can write dot product as a matrix multiplication like this, in which the result will be a 1 by 1 matrix, for example. If both of them were 4 by 1, 4 by 1, this will be 1 by 4 multiplied with 4 by 1. It's going to be 1 by 1 at the end. Okay, so this is true when they're column matrices. If otherwise, it will be difficult. It might end up with a 4 by 4 matrix. This is when these are like column vectors, as we have seen before. So when this becomes 1 by 4, you take the transpose. This is how you can write dot product as a matrix multiplication. So if you do the same thing with the transform V prime, in which you write the transpose of it. So this is the transform V coordinate is given this one. And since we know this N prime T, the transpose of N prime T is given by this Z, we are going to multiply our normal vector with the Z to figure that out. And as you can see, they're reversed in order because actually Z is multiplied by N, but the transpose of this has the multiplication like this. And if this one is identity, the relationship will be preserved. If you have an identity matrix, then this N times V is exactly the same as this N transpose V here. We want this to be identity matrix to preserve the relationship. So in other words, M is the inverse of the transpose of the modeling matrix in order to be an identity matrix. So therefore this Z matrix is given by the transpose of the inverse of this matrix M. And since this is a square matrix, what we do is we can first take the transpose of this 4 by 4 matrix, then invert it. And in practice, since we don't want to translate the normals as well, you remember we had the homogeneous coordinates 0 in the beginning of this slide, somewhere in 2D, yeah, right here in slide 12, we set the homogeneous coordinate of 0. And the way we actually do that for normal vectors is, instead of having their fourth dimension 0, we just use normals as three-dimensional vectors. We don't need to have homogeneous coordinates for them. And this matrix that we will be using for is, when we're computing this, and we just use the top 3 by 3 portion, the last row and the last column, which you also asked last time, saying, do we ignore that last column and last row in these modeling transformations? This is always 0, 0, 1 and 0, 0, 1 in both cases. For transforming normals, we actually completely get rid of that part and take the only top 3 by 3 example. So here, yeah, this one actually, the transforming normals ends up here. So we take the top 3 by 3 and the inverse of that is going to give us, the transpose of the inverse of that will give us the normal transformation matrix. Yeah, up to now we have used as coordinates and vertices, we have used column vectors, which forced us to do multiplication on the left like this. But there are other systems in other books, or maybe in some other computer graphics systems, you may see that the coordinates are represented as row vectors, and in that case we will have to multiply. Our rotation matrix are going to be right multiplied, but everything in that case should be transposed. All those rotation UV axis, UV W axis, they have to be represented in this column major order. So the transpose of this should be your rotation matrix. And yeah, when we have a rotation matrix like this, this is our 2D rotation matrix. When we transform the object by this matrix, it will not change its shape. If we also add a translation, rotation, they do not change the shape. So rotation and translation, they do not change the shape of the object at all. Okay, the shape will not be affected by rotation and translation. These are sometimes therefore called rigid body transformations because they do not modify the shape of the object. So therefore rotation and translation, sometimes in the literature, they're called rigid body transformations. And uniform scale also is going to preserve the angles. When you do uniform scale of an object, it's also going to preserve the certain properties of the object. Your object will get smaller. Its volume is not going to be preserved. But with rigid body transformation, just rotation and translation, everything, I mean, its volume, surface area, the respective angles, the distance of points to each other, everything is preserved in rotation and translation. But with scaling, with uniform scaling, some of these properties are preserved, but like the surface volume is going to get smaller, or the surface area or the volume is going to get smaller if you make the object smaller. And there's also, and here's when we add scaling, the object, the matrix may look like this. This is in 2D. But we add scaling, it's not going to be, this ABCD may not necessarily be orthogonal to each other anymore. They will also contain the effect of rotation, scaling, everything will be combined here. And if we just have a rotation matrix, an arbitrary rotation matrix, sometimes they will not preserve the original shape, but they, as I said, they may preserve certain things like the angles or lines being parallel, remaining parallel to each other. In such kind of transformations, which are done with these matrices, are also called sometimes affine transformations, which is an arbitrary sequence of rotation, translation, scaling, and shearing. So any linear transformation with the help of these matrices are also in literature. If you read later this affine transformation terminology, it just means that it's using this matrix multiplication, which is a linear transformation of your points. Now, The last row of the matrix, as you can see, it's just 0, 0, 1. We haven't used it at all, but especially these two values 0, 0. In projection transformations, we are going to see they will not remain 0, 0. It will help us to make these divisions, which are non-linear. So they're not, this projection transformation is not affine transformation. It's because what you're doing is something non-linear. You're dividing x, you find x prime by dividing x with z, which is also a variable. We will be able to achieve it in the last, by changing the last column of this transformation matrix. So this concludes modeling transformations. Oh, shearing is this transformation x's. Let me just quickly write here. Remember the deck of cards thing? The deck of cards, they're just, for example, if you have a rectangle like this, when you transform it, it becomes something like this. So it's like your x prime is given by x plus some dy, for example. That's the shear transform. A transform which I haven't used at all. There's no, for example, there's no function for that in OpenGL. So mostly when you're doing game programming or any animation or any simulation, these rotation, translation, and scaling are the main transformations that you need. So these are the most important and most widely used transformation, and you can do everything with these most of the time. And we are going to start viewing transformations on Tuesday, but actually I just want to show you a quick heads up we actually know how to do camera transformation with the alternative method of rotation. Now, here is what we'll try to achieve. Imagine, let me show it on 2D first. Imagine this is my coordinate system, and I want to move it to change it to a new coordinate system in which I have, for example, this is my x, this is my y. So let's call them x prime, y prime. This is my new coordinate system, and this is the new origin. So this origin, for example, 1, 2, 3, 4, for example, it may be 4, 4, 2. Look at this origin. I want my new origin to be 4, 2. I want my new x prime to be this 1, 0, and this is x prime, and my y prime is, sorry, it's 0, 1, not 1, 0. 0, 1 is my 0, 1 is my x prime, and minus 1, 0 is my y prime. So this is a new coordinate system with origin at 4, 2. Now, here's the question that we'll be asking. Imagine a point which is somewhere here with a coordinate, for example, 3, 3. Okay, in the world coordinate system, this point has a coordinate 3, 3. If I change from world coordinate system, let's call this camera coordinate system, a new coordinate system in which the camera's eye point is at 4, 2, and its gaze, or I mean, it's everything, its local coordinate axes are different. It's given as its x prime coordinate is 0, 1, its y prime is minus 1, 0. So this is the new coordinate system. If we change the address of this point from world coordinate system to camera coordinate system, what will this 3, 3 be in the new addressing system? This is the question that we will be answering. And actually you can find, right? I mean, what will be the coordinate? If you just bend your head, I mean, tilt your head like this, you can find that, oh, its distance from this 2 is 1. Its x coordinate, I think, is going to be 1, right? So it's going to be 1 and 1, 1, 1. Is it going to be 1, 1? I think so, right? I mean, this is 4, 2. X is like this. I think this is going to be 1, 1. Its distance from this is 1 unit above, 1 unit to the right. Yeah, it will be, its new coordinate is going to be 1, 1. Now, our goal will be to figure out this matrix, world coordinate to the camera coordinate transformation matrix, okay, multiply it with this 331, this 33, and which will give us this new 111. How can we figure this out? How can we find this matrix? Is by just given these parameters, the new origin and this one. How can we find this? Will be our the thing that we'll solve. And the way we are going to do is align this coordinate system. In order to achieve this, we need to do the transformations to align CCS on top of VCS. So that's a little bit counterintuitive, right? I mean, we are going WCS to CCS, world coordinate system to camera coordinate system. Shouldn't we write the transformation to align this one on top of this one? No. You can actually check. We can try both of them on this example. The solution, let me tell you again, is in order to find this transformation, what we need to do is write the transformation matrix such that we align this one on top of WCS. So what is that matrix? How can we align this on top of this one? It's easy, right? Transform -4, -2. Yeah, translate. If I translate this, first move the origin to this origin. So it becomes like this. This is y prime, this is x prime. Okay, so I translate it here. And if I rotate around this pivot point -90 degrees, so if you rotate -90 degrees around origin, x prime is going to be this, y prime is going to be this. If you rotate 90 degrees in clockwise direction, if you rotate 90 degrees, you find it. You may try this. We already know in 2D the translation matrices and rotation matrices, right? Form these one. Actually, we can do that easily. Also, form these 3x3 matrices: 1, 0, -4, 0, 1, -2, 0, 0, 1. What is rotation matrix? 90 degree. So cosine 90 is 0. Minus sine minus 90. It's going to be, so I think this is going to be 1, right? Because sine minus 90 is -1. It was cosine minus sine theta. There's a minus also in front of it. It's going to be 1 like this. Then sine minus theta, this is going to be -1, 0, 0, 0, 0, 1. So multiply these two matrices. That will be your world coordinate to camera coordinate system transformation. You may try this out. Check this out. You may watch this video later, this part, and check this out. Find the multiplication of these two matrices, R and T matrices, and try to multiply it with 3, 3, 1, whether you get 1, 1, 1. Then interesting thing is you may try it with any other point in the world coordinate system. Multiply it with your this will give you the new address of your point in this new coordinate system. So this is the first part we will be looking at, and we are going to see how we can do it in 3D, but it will be very similar to this example. We'll continue doing these things on next week. And rotation. Yeah, exactly. So here rotation gives exactly the same as the alternative method. Oh, look at these. They are 0, 1 is my, yeah, I just use cosine and sine, but the vectors were already given here, right? Why did I try to do the rotation matrix? The coordinate system is already given by this as basis vectors. You could as well write them. That's exactly what we are going to do. Actually, I just missed that out. It wasn't by intention, but you figured it out that it was good that you code this. We could directly, why do we try to use cosine sine? Especially in 3D, we'll need to do 2 rotations, right? I mean, if I was to do this 3D by using angles, I have to do 2 rotations. A single rotation would not be sufficient. But if the alternative method, directly, whatever your x prime, y prime, z prime vectors are, just write them here and that's it. You're done. You don't need to undo anything. There's no undoing here. You just you align your coordinate system on the world coordinate system. That's your world coordinate system to the camera coordinate system transformation matrix. Okay, so very good point. All right, that's it from me for today. Let me stop recording.